Okay, so this session is actually quite short, it's 70 minutes or something. So there were two problems left, I think, from the previous session. So let me first go through them. You refresh your memory a little bit. And then we also want to talk a new topic, which is of course included in the same page in the book. So the book is actually doing great. So they are teaching all this stuff in one page, okay? But anyway, these are very important things. So this is also another important topic, rational expressions. Again, this is not totally new for you. You know something about this from Math 1C, but here we now want to make it a little bit more complete, okay? But before doing that, let me bring you the examples. So if you remember, to make it a little bit smaller, we were supposed to factorize these polynomials as much as possible, yes? So these are what are left from this session. Yeah, something like this. So let us do these, okay? I don't know, if you haven't thought about the problem before, I think it would be good if I give you 5 minutes so that you think about these problems yourself first, then I will come back and solve this problem for you, okay? So I will give you 5 minutes. Please try to think about these problems. Okay, so let me start solving them. Hopefully you succeeded to solve these simple problems, yes? Then the last one is a little bit interesting, but I don't think you face a big problem here. So do you remember we were talking about a conjugate pattern to help us to factorize polynomials, meaning to write them as a product. So the conjugate pattern, you need to have something like this in your head. You have the difference of two complete squares. Then if that's the case, you can write it as this expression, yes? So that is the conjugate pattern. But how we get suspicious about that if this is going to be solved using the conjugate pattern is that I should have the difference of two complete squares. Of course, here you have the difference, you have two terms, but none of them is complete square, yeah, is a complete square. Then if you remember, let me go back. So if you remember, I had a remark for you here from two sessions, I don't know, from that session, that if you can factor the highest common factor, and if it is applicable to all the terms involved in the polynomial, this will have the priority. So try to remember this remark by heart, okay? So then I will use this one here because I immediately see that I can pull something out. There is a common factor between these two terms, yeah? So if I want to solve the problem, I would say f. So f is actually the first step that I will do. Okay, can you help me to do that? What should I do?
You can pull out AX.
AX, exactly. So I pull out AX, and what is left for me in the first one? It is 121 A squared. And what is left for me in the second one? It is 49 x to the 2. Okay, so at least this is partially done, because if I ask you, is this a product form? You would say, yes, this is the product of three terms, A, X, and the whole expression. If you stop here, and if it is possible to continue more, then of course you will lose some points. And here in this case, it is possible because immediately you realize that these two are complete squares, yes? So if you want to, you can write it, you can write an intermediate step. It's not mandatory. Instead of 121a squared, I can immediately write a 11a to the power of 2, yes, because 11 to the 2 becomes 121 and a to the 2 becomes a squared. For the same reason, I can write the second one in this form, 7x to the 2. Okay, so then immediately you see that you have the difference of two complete squares. It reminds me of the conjugate pattern. So what can I do? I can write ax, I open two pair of brackets, I take the square root of the first one and put it here. So it becomes 11a, 111a here, 111 here, 111a there, and then 7x here and there. And then I choose one of them to be positive, one of them to be negative, and it doesn't matter which one is which. So this is the full factorized form of this expression. Any questions? Okay, let us go to part G. So part G, the same story. I have the difference of two terms. None of them is a complete square. Either it is not possible to factorize it at all, or if it is, might be I should be able to pull out something. And it's clear that I can pull what out from these two?
Pull me, daddy.
Pardon? So what can I pull out from these two terms?
3x.
Yeah, 3x, thank you. So this becomes 3x, and then I will have how much? I will have x to the 4, and then I will have minus 16 y to the 4. Yes? But immediately, even though this is done partially, it is not complete yet, because x to the 4 is the square of x to the 2, and 16 y to the 4 is 4y to the 2 squared. Okay, and then I immediately realize the conjugate pattern, so it becomes 3x, and then I open two pair of brackets, take the square root of the first one is x squared, I put one x squared here and one there, and then take the square root of the second one is 4y squared, I put one here, one there, one of them negative, one of them is positive. Okay, do you think the problem is finished or still I can continue?
I think it's finished.
Anyone else?
But since you asked the question, I guess you can continue.
Yes. So this is being a psychologist, yes. Okay, but anyway, any opinion? Can I continue or not?
Well,
Do you see any other conjugate pattern involving here? Is the last one a conjugate pattern?
Yeah, you can do it like again. So you can, so like in that case it would be 3x times x plus 2y times x minus 2y times x squared plus, did I write
Yes,
4y
that's
squared, I
correct.
think.
Yeah. But why do you think, so you say that this is a conjugate pattern, but this is not, because if I remember, you were reading it in the same way. Yes, you are right. This is a conjugate pattern, because again, this is a complete square. This is also a complete square, and that's the difference between two complete squares. Here, even though these are complete squares, but this is the sum of two complete squares, which is not the conjugate pattern. Okay, so if you stop here, again, it is not complete. So this becomes equal to, I write 3x, I open two pair of brackets because I realize that this is a conjugate pattern. This is not a conjugate pattern. So the last one should be copied and pasted. But here, I know that if I take the square root of this one, by the way, if you don't understand, let me write it in this way. So 4y to the 2 is just another name for 2y squared. So this is a complete square, and this is a complete square. So what I do, I take the square root of the first one, of the second one, and one of them with negative, one of them with positive. So you see, this simple problem was very interesting because this is the complete factorization. By the way, let me repeat again, I am not simplifying things at all. Actually, I'm making things more complicated. Yes, this one is much longer to write than this one. If someone asks you, are these two equal? Definitely yes. Which one is simpler to write? Definitely this one. So what is the benefit of factorizing? It becomes clear later. Factorizing a polynomial is a very powerful tool in our hand. For example, if we want to solve higher degree equations, this is one way we can do. If we want to simplify rational expression, which is one topic for today's lesson, factorizing polynomials are easier. So be careful. You are not, first of all, allowed to multiply this back. Definitely, if you multiply this back and say spend a lot of time, you will get the same answer. So that is not the goal. The goal is to write your expression in a product form, even if the product form is more complicated or longer, more tedious than the original one. Don't worry about that. Here, simplification is not the point. Here, writing the expression as a product form is the point. Okay, and finally, the reason that I gave you this example, because I want you to broaden your point of view a little bit. Any one of you have a suggestion for this one? Do you see any kind of pattern?
For H?
Yes?
Well, yes, you can. Well, 16 is a square of 4, and you can just take away the 2 there from the brackets,
exactly.
and you get it.
Exactly. So this is why I'm saying it might be some of you are asking yourself that isn't it a squaring pattern? Because you are just thinking here. Yes, of course. If I want to expand, I have to, or I can use squaring pattern. But my goal is not expanding. My goal is to write the whole expression as a product. This is not a product because this is difference between these two. So don't get confused. Let me write and then I will clean it. If someone tells me that I can write this expression, I would say the first one to the 2 times the first one times the second one with the negative sign, because this is the second version, and the second one to the 2. And then at the end, I have a minus 16. And if I write it in this form, you see, I use one of the versions of a squaring pattern with the negative sign. The first one to the 2 minus 2 times the first one times the second one plus the second one to the 2. And this minus sign, I just wrote it down. And then if I multiply this, this becomes this. If I raise it to power 2, it becomes this. If someone tells me that, is it wrong to say this is equal to this? Of course not. This is exactly equal to this. But the problem is that this is not the point of this exercise. The point of this exercise is to write this, if possible, of this expression in the form of a product. This is not of a product yet. So don't get confused. Here, our goal is to write as a product. Even though this equality is 100% correct, but this is not the answer to this particular problem here. I hope that I could make myself clear. So don't get confused. Okay, so now the goal was to factorize, and then I will use what Rocco actually mentioned, and it was very nice. So you see that you can immediately recognize the conjugate pattern again. If you are not comfortable with that, let me just write it. The first one is of course clear. You yourself see that this is a complete square. This is this expression to power 2. 16 also is very familiar for you. Yes, that's also a complete square. So I can write it as 4 to the 2. Then what I have this one to the 2 minus this one to the 2. And if you do not look inside, this should look familiar for you. Yes, that's a conjugate pattern. So I will open 2 pair of brackets. I will find the square root of this. The square root of this is just simply I take 2 away. So I put it here and here. And then the square root of the other one is 4. But one of them is negative, the other one is positive. But nobody leaves this in this form. These two pairs of brackets are important, but this pair of brackets is not necessary at all. It's not separating something from something, yes, because there is nothing behind that. So let us remove that pair of brackets. This is mandatory to remove that. I don't really like if you write it like this and leave it, even though technically it is right. But it means that you don't appreciate that you need to take away what is redundant, what is not necessary, yes? So I would write it as in this form. I would write x squared minus 4x minus 4. And then I will have x squared minus 4x plus 4. So did I succeed to write it as a product? Yes, I wrote it as this product. But you need to have always this suspicion that might be this is not complete. But what do you think? Do you think it's complete, or I can continue more?
You can use the squaring pattern for
Exactly.
yeah.
A squaring pattern in which one?
On the second one. You can't use it on the first one because it's all minus, but you can use it on the second one.
Exactly. Okay, so I will continue. So I will copy and paste this one. And then, do you remember, this is a squaring pattern. Why? Let me repeat. We have three terms involved, one criterion. The other criterion is that I have two completed squares. But the third one, which is also important, you need to check is that, is the middle one the appropriate one? Meaning that I take the square root of this, it becomes x. I take the square root of this, it becomes 2. And then I multiply it to myself, it becomes 4x. And 4x is exactly this middle term. So yes, this is a squaring pattern. So what I do, I put a pair of brackets with power 2 on top. I take the square root of the first one, it becomes x. I take the square root of the second one, it becomes 2. But this is the negative version of a squaring pattern. So this becomes minus 2. And here is the end of the problem. Okay. So hopefully this is, so I think that is even more than enough. So these are probably higher level questions for the exam. Might be, we can call them A-level questions. But then, if you remember, there was also one more problem left. So let me make it a little bit bigger so that you can read it and bring it here. So this is example 5.3, the third example of the fifth session, I mean, by 5.3.
Babak?
Yes?
I think you said there were two or one more problem also.
Where?
When we, last lesson, when we did factoring polynomials, in the end of the lesson, we did a bunch of examples like A to L. And you said we're gonna do L together or something.
Okay.
Exactly,
Thank
those
you.
questions.
Yeah, this L you mean here on the page now, yes?
Yeah.
So J, K, and L. Yes, that's good to remind me here.
Okay.
Okay. But let me finish. That is good. I have forgotten that. Okay. So let us for the time being concentrate on this problem that I wrote here. So without using a calculator, determine the value of this. 202 to the 202 squared minus 192 squared. Of course, this is not a very hard problem. Even if you don't have calculator, you need to spend some time, calculate this by hand, and subtract them. But hopefully you can realize there is a nice pattern going on, and might be using that pattern can solve the problem simpler for me. Yes, do you see that?
Yes, it's conjugate pattern.
It's conjugate pattern. Might be the conjugate pattern is helpful here. Let us test it. There is no guarantee, of course, but let us test it. This is the conjugate pattern. So the answer becomes 202 minus 198, and then multiplied by 202 plus 198. I hope that every one of you understand that this is exactly the conjugate pattern. But is it useful here? Yes, because the difference here is small. The difference between these two numbers is just 4. And then the sum is not also hard to calculate in your head. What's the answer?
Sorry, what?
What is the answer to this one in your head?
400.
It's not hard. 400. So, and then multiplying 4 by 400 is also very simple. So it is 1600. And as simple as that, you see, I really didn't need any calculators. I was able to calculate this numerical value very quickly. Okay, so that's also one benefit of knowing these patterns. But most of the time, when we have these kind of numbers, we can use calculator to calculate them. But of course, GeoGebra is also capable of giving you this factorized form. By the way, I think that would be a good idea if I can show this here to you, that if GeoGebra, how we can use that. Let me do this. That is also good. Then we go to the next lesson, or better, it is better to go to the next lesson first. Yes, let us go to the next lesson first, because I just want to Fine. All right. So, Gustav, I will come back to those exercises left there later,
Okay.
okay? So let me just give you another, I want to teach you the new lesson, which is not a new lesson. This is just a repetition from Math to Math 1C. And I want to talk about rational expressions. So what do I mean by rational expression? A rational expression is a fraction whose numerator is a polynomial and its denominator is also a polynomial. Every expression like this is called a rational expression or algebraic rational expression, if I want to be precise. So algebraic rational expression means a fraction of the following form. Here, a polynomial is in the numerator divided by another polynomial in the denominator. Okay, so let me go back to the very elementary lesson. If I give you a fraction of numbers, not just polynomials, of course, numbers are also a specific form of polynomials in which no variables are involved. But if I give you this fraction, say, for example, 14 divided by 63. If I want to simplify this fraction, of course, this is simple, that might be you are able to do it in your head, but in principle, you have to factorize 14 and then write it 2 times 7 and factorize 63. You can write it as 7 times 9. And then you have to find the highest common factor and cancel it out. Yes? And then you get 2 over 9. Of course, you might do it very quickly in your head and just write the answer, but the reason that you divide the numerator and the denominator by 7, for example, why don't you divide the numerator and the denominator by 12? Why do you choose 7? In principle, I can divide everything by 12. So why do you think I choose 7? Because 7 is a common factor. Yes? So it means that I can divide by common factors. If I divide by something which is not a factor, it is still doable. If someone writes this and say that these two are equal, yes, that's correct. But this is making things harder. If someone tells you that, okay, is this simpler than this one? You don't accept that. This is even harder. So even though technically we can divide by something which is not a factor, as far as I divide the numerator and the denominator simultaneously by that number, but we don't do that because if we do, we are making life harder for ourselves. Then we have to work with this mixed fraction. So, but if I divide by the factor, the whole point is that because this is divisible by the factor, this is also divisible by the factor, I will get I will get a simpler expression than before. And of course, it is clear that if I want to don't face with mixed fractions, the factor that I am eliminating should be a common factor. For example, if I divide by 2, even though the numerator becomes 7, but the denominator is not divisible by 2, it remains 63 over 2. So still I have a mixed fraction. So this is why I have to have a common factor to eliminate that common factor. And of course, if I want to make it as simpler as possible, I have to pull out as highest common factor as possible. Okay? This was for numbers. For polynomials, we have to factorize them using the tricks and techniques that we learned for factorizing polynomials. Yes? So this is why this lesson is nothing except 2 factorization problem and learning how to cancel factors. Okay, so if I give you a polynomial and to divide it by another polynomial, which is a rational expression, and I ask you to simplify, it seems that I am giving you two factorization problems. A factorization of the numerator, a factorization of the denominator, and then learn how to simplify common factors. So this is why learning factorization is crucial for many lessons coming after this, even for the next year. So try to learn identities, squaring pattern, conjugate pattern, how to use them to factorize polynomials, how to factor a common factor out, and then especially the pinnacle of that expression is how to simplify a fraction, including polynomials. Please try to solve as many problems as you can for this, and I will try to make some videos related to this for more interested students. Okay, now after that, let me give you this example. We start solving the problem together, okay? So this is the typical example that I want you to solve. Might be we will not. Okay, I can copy and paste it on the next page as well. So I have enough space, more or less enough space here. Oops. Okay, so here, simplify the following fractions, or instead of fractions, I can call rational expressions or algebraic rational expressions. So here I want to start simplifying this. The first few examples are very simple. Already they are in factorized form. Is the numerator in the factorized form? Yes. Is the denominator in the factorized form? Yes. So if I want you to simplify a rational expression, your duty is to fully factorize the numerator, fully factorize the denominator, and then remove the common factors. These are the things that you need to do. Okay, so let us do it together, okay? Part A. This can be written as, of course, I am making things a little bit harder. You really don't need to write here. I factorize 15. It is 3 times 5. And I have x and I have y. You really don't need to write 3 times 5. You can do it in your head. And instead of 25, I can write 5 times 5, or 5 to the 2. And then I have y. So this is already in factorized form. This is already in factorized form. And if I ask you what are the factors of the numerator, you would say 3, 5, x, and y. If I ask you what are the factors of the denominator, you say 5 and y. So you see I have one common factor here and one common factor here. These can be canceled out. And then 3 and x, 5 are left. So I will do it like this. So I would say that, okay, this 5 and this 5 are gone. Even though I use cancel out or gone, but what do I mean by this? I don't mean it is 0. Remember, here, there are two ways. When I say gone, I would say 5 minus 5. I would say 5 and 5 are gone, but of course here the answer is 0. But if I say here 5 and 5, 5 and 5 are gone, the answer is not 0. The answer is
1.
1.
So be careful. Yeah, I'm just sloppy a little bit when I'm using this. So here I would also say 5 and 5 are gone, or here. But here I am dividing. In the first one, I am subtracting. So if I want to emphasize that, I put a 1 on top here, and I put a 1 on top here, because I'm dividing the numerator and denominator by 5. And again, I am dividing the numerator by y, the denominator by y as well. So let me write this. So what is left for me is 3 times 1 times x times 1. I will never ever do like this. It is tedious. I just want to solve the first example here in this way. Okay, and then I will answer this more properly in the numerator. Now after simplification is done, I multiply everything back. The answer is 3 times 1 times x times 1 is 3x, and the next answer is just 5. So that is the simplified version of that fraction. Okay, let me just tell you one crucial point. If I ask you, do you believe that this expression given in the problem is equal to this expression always, what's your answer?
Yes.
Any other opinion? If you solve this in the exam, for me, this is totally correct, but I want you draw your attention to some very important point. If I ask you, can you calculate this for x equal to 1, x equal to 1, y equal to 2, you would say, yes, I will put x equal to 1, y equal to 2 and solve it. If you put x, and then if you calculate this one, you will get the same answer. But this expression, if I ask you to calculate it for y equal to 0, then you will have problem. Even though you don't have any problem for y equal to 0 here in this case, because there is no y involved. So I would say that this is equal to this if I respect the domain of validity, yes? It means that y shouldn't be equal to 0. So this expression is always equal to this expression under the condition that these two expressions are well defined in the first place. This is always well defined. This is always well defined because the denominator is 5 and 5 cannot be 0 at all. But this one can be 0 if I choose y equal to 0. So it means that this equality between these two is limited for those values of y which y is not equal to 0, for non-zero values of y. But you don't need to be worried, but I want you to understand that when we say this is equal to this one, it's not 100% correct. We should say that this is equal to this one if y is not equal to 0. This is more or less always implicit in this calculation. Yes, we always assume that what we have in the original version and what we are get for the answer are well defined. When they are well defined, we say that they are equal. So have this crucial point in mind. Okay, so let us do number B very quickly because it's very simple. So part B. So let me write them below each other. This might be better. Anyway, I will not be able to fit everything here. So part B. So what should I write? I would write this is equal to, let me write this here, 7 over 21 x squared y to the 3. What is the only thing that I can cancel out? I can divide the numerator by 7, minus 1 is left. I can divide the denominator here by 7, 3 is left. Nothing else can be simplified. So what is left for me is a minus 1 in the numerator and 3x squared y cubed in the denominator. Yes? Okay, I can also solve C here. Yes, questions?
No, I just said yes.
Okay, C here, what should I do? Let me just write it again. So this is equal to minus 35 8 squared b to the 4, and then I have minus 63 a to the 4 b to the 2. So first of all, can I simplify? By the way, I remember I forgot to say here, everything should be in factorized form. So yes, it is in factorized form, so I can start immediately canceling things out. Yes. Okay, so what I do in the numerator, I divide by minus 7, it becomes 5. Or if you want, you can say that, okay, minus by minus, they are simplified. And then I can divide this by minus 7, it becomes positive 9. And this a squared divided by a squared, it becomes 1. But a4 divided by a squared is left. And then this b squared by b squared is 1. Here, b squared is left. To fix this mess, let me write everything clearly. I am left with 1, 5, 1, 1, and b squared. In the denominator, I am left with 9, a squared, and 1. So if I want to write it simpler, I would write 5b squared divided by 9a squared. So that is part C. Now, the interesting things happens from this exercise. Now, part D. So this is very important. I have seen students make a lot of mistakes. Hopefully, I can teach you. In my 25 years, more than 25 years of teaching, I was not able to teach this part properly because every now and then I see many students make mistakes. Okay. The first thing is that some of you are, don't know, for some reason are tempted to simplify these two. So this is not the case. Because remember this in mind, only common factors can be simplified. So let me write this with red something. Only common factors not summands can be cancelled out. Oops, cancelled out. I don't know, in American spelling, cancelled is with one L or double L?
It's one L.
One L.
Yeah, I think in British one is double L, so let us stick to the American one. So, and not summands can be cancelled out from the numerator and the denominator. Okay, so I think this is not a very good place for this. Let me make it a little bit smaller. Yes, and I can put it here. So this is very, very important. So don't be tempted to to simplify this x with that x. No. To simplify this 4 with that 4. No, unless you have a reason for that. The reason should be that that is going to be canceled should be a factor. Okay. So if I ask you, is it in factorized form? Because if you want to realize what are the factors, there is one thing to do. Factorize it first, and then everything that you see in the factorized form are factors. So is this in factorized form? Clearly not. So what I can do, I can factorize it. Okay, this should be a very simple problem for you now. How should I factorize the numerator?
X times x plus 2 times 2 times x.
No, in the numerator, there are two terms. How should I factorize it?
Is the numerator the top one?
Yes.
Okay, you take out 1x.
Exactly. So I don't know, I hope that you haven't forgotten. So this is why these lessons are actually very highly dependent on the previous lessons. So if you don't understand, please let me know. Is there any way to factorize the denominator? By the experience you gained so far, if you have done your practice well, it means that no, you know that x plus 4 cannot be factorized anymore. Okay, now I ask you, what are the factors of the numerator? So let me write it here. Factors of the numerator. What are they? Name them.
Like x and bracket x plus 4.
Yes, let us just write x plus 4. And then what are the factors of the denominator?
I don't know how to explain it, but maybe you can say like 1 times x plus 4, and then you can cancel x plus
exactly,
4.
But
is
you
that
don't,
right?
That's correct, but is exactly like this. When I ask you what are the factors of 7, how do you answer?
It's
Prime
1 and
number.
7.
What Rocco said is also correct for here. People can say 1 times 7. But if it is not necessary, we can just write it 7. So, but if I ask you what are the factors of 12, you can say 2, 2, and 3, okay? So this is the case. So you don't need to write 1 and x plus 4, but even technically you are right, but yeah, you don't need to be that precise. So here I have only one factor, and that is x plus 4. Now in this list and in this list, you see, you understand now why 4 and 4 cannot be cancelled. Because if I ask you what are the factors of the denominator, you will tell me this package as a whole is a factor. And the packages here is one of them is this one, the other one is this one. Then you see that the whole package here is in common. This as a whole can be simplified, not individual parts of each of one of these factors. So this means that I can safely remove this x plus 4 and x plus 4. Of course, when I simplify it, it means that 1 is left from here because I'm dividing. And then if I want to write it one more step, it becomes x times 1 divided by 1. You really don't need to write this step, and it's better not to write it. So the answer is simply x. So this is very crucial. This is a simple exercise, but it's a prototype example. You need to remember, you are not, am I allowed to simplify this x with one of these x's? No. Am I simplify this x with that x there? You might say that, okay, this is a factor. No, this is not a factor. This is a factor only for this part, not for the whole expression. And can I simplify this 4 with that 4? No. You say that this is 4 is multiplied, so it's a factor. No, it's a factor for this again, not for the whole expression. So you see, you shouldn't be lazy to think in this way. You need to think in this way over and over again so that you can do it very quickly. This is the analysis you need to do. Factorize, and then tell me the factors, and then find the common factors, and then cancel the whole package of a common factor out. This is the only way that you can simplify. So let me just ask you one question. Do you think if I have this expression, I have seen this many, many times, can I simplify this x with that x?
No.
Yes or no?
No.
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 Why? Because x is not a factor, it's a summand, yes? If I ask you read this expression, you say that this is the sum of x with 4. When you say this is a sum, it means that these are not factors unless the whole package can be simplified, which is not the case. So be careful, you are not allowed to simplify this x with that x. If I give you this to simplify this, you don't write anything at all in front of it. It cannot be simplified more. Of course, if you want, you can write it as x divided by x plus 4 divided by x. And then can I simplify this x with that x here now? Come on, yes or no?
Yes.
Yes.
Yeah, here you can simplify because these are the only expressions in the numerator and the denominator. Any fraction whose numerator and denominator are the same is 1. So this is 1, and then unfortunately it remains 4 over x. So in this lesson, when I ask you to simplify this, I don't mean you to do this. So forget about this. If this, you need to know that this is not possible to simplify it more. Even though if you do this, I wouldn't consider the simplified version. We don't consider this the simplified version, but this is completely correct if you do it in this way. This is also correct, leave it like this. But if you attempt to simplify these two, then that's wrong. And one technical question again, do you agree that this expression is always equal to this expression? Yes or no?
Yes.
Yes or no?
Yes.
No?
Unless x is minus 4.
Exactly. So even though you don't explain it at all in the exam or whatever, but I want you to understand that if someone tells you that this expression is always equal to this, you would say that, okay, 99.999% yes, only one case, no, and when x is equal to minus 4. X equal to minus 4, the right-hand side becomes minus 4, but the left-hand side doesn't make sense at all. So I cannot say that minus 4 is equal to nonsense, yes? So you remember that when we simplify, implicitly we are assuming that both of them are well-defined. In that case, they are equal. Okay. So let us go quickly to part E. What do you think if you start doing E and F yourself first, huh?
Let me ask first. Did you skip C on purpose, or did you miss?
No,
Because we
C
did
is
a D,
here.
right?
No, C is here. You see that?
Wait, where is? Ah, there.
Marco,
Okay.
you blind.
Yeah.
Sorry.
Okay, no problem. Okay, so I will pause the video. Hopefully you can do these two at least yourself. Okay, 4 minutes is good because the lesson is finished actually. We need to do more exercises. Okay. Could you solve the first one, part E?
No.
Okay,
I
so let
think
us see
so.
why not. Anyone solve the problem?
No,
None
I
of you?
couldn't do it.
Why not? So let us see why not. There is nothing difficult in this problem. I told you that if you want to simplify, you need to fully factorize the numerator and the denominator separately. So it seems that I wouldn't believe that if I give you this, I ask you to factorize. Can you do it or
Wait.
not?
I know I found I know what to do.
Can I say the answer
Can I
I
say?
got?
No, this is the
After you,
problem.
Rocco.
The reason is that you don't listen. You need to listen what I'm saying. It is not hard because you need to break the problem into two simpler parts. I want to factorize this. Can I do that? Yes. Can I factorize the denominator? This is the probably possible, simplest possible conjugate pattern problem. Yes. So this is what I'm saying. You need to take lesson. If you think that if the form of the problem becomes complicated, you have to lose the problem, that's not the case. You need to change the way that you look at the problem. If the problem is harder, you need to train yourself to break it into simpler parts. Okay, so you shouldn't give up. I would say that I want to simplify this. I know the rule, and I know why the rule is helpful. I factorize the numerator. When I am factorizing the numerator, I have trained myself. I don't care about the denominator at all. Okay, so what I do, I ask myself, can I factorize the numerator? Only this problem. And then I'm completely sure that all of you could do actually this factorization. It's so simple.
Yeah.
And now when I am doing the denominator, I totally forget about the numerator. I ask myself, can I factorize this?
Use conjugate pattern.
It's a conjugate pattern because it's a difference of two complete squares. So I have two pair of brackets, x here and there, 3 here and there, one of them negative, one of them positive. Now the first step is done. At least you get 1 point. But now, is there something that I can simplify? I need to ask myself, what are the factors of the numerator? You need to name them sometimes so that you get used to it, so that you can do it quickly. These are the only factors available for me in the numerator. But if I ask you what are the factors in the denominator, you would say this is x minus 3 and x plus 3, yes? Now, is anything from this list exactly identical to one of these? It's clear.
X minus
3 is exactly identical. So this can be eliminated. Yes? So what I say, I will eliminate this. It becomes 1. With this one, it becomes 1. And then what is left for me? In the numerator, I have x times 1, but nobody writes x times 1. We write simpler this one. In principle, I am left with this one in the denominator because any expression multiplied by 1 is itself. Here, having this pair of brackets was crucial, but there is no role for these pair of brackets anymore. So it's much better to remove what is not necessary. Yes? Now my question for you, can I simplify this x with that x?
No.
No. Why? Because this x is of course a factor for the numerator. It's the whole expression in the numerator, but this is not a factor, that's a summand. So this is the end of the problem. Okay. Any questions so far?
No.
Okay. Now the same thing happens here. I don't know. Could you solve this one?
Yes.
Yes. What should I do for the numerator?
You should put it back into the pattern. What was it called?
The squaring pattern, you mean?
Exactly.
Yes. The reason is that, why should I get suspicious to this? Because I have 3 terms. 2 of them are complete squares. Take the square root of this one is 2n. Take the square root of this one is 3. Multiply them, multiply by an extra 2. The answer becomes exactly 12n, and 12n is the middle term. Yes. So I put a pair of brackets with the power of 2. Take the square root of the first one. Take the square root of the second one. This is the positive version of the squaring pattern, so it becomes positive. And then I have 2n plus 3. Okay? Now, if I ask you how many factors you see in the numerator,
2.
in the top one, 2. But both of them are the same.
Yes.
2n plus 3 and 2n plus 3. What do you say? What do you see as the factor in the denominator?
2n plus 3.
Yes. Is there
Yes.
something exactly in common? Yes. So this can be canceled. So this means that I can divide this by itself. It becomes 1. If I divide this, one of these are gone. Yes, I had 2 of them. One of them is canceled out. So one of them is left. So in principle, I can write it as 2n plus 3 divided by 1, but nobody writes something like this because there is a simpler way of writing this. That's the end of this problem. Okay. Okay, so by the way, I don't know, all of you know that I will put these notes below the videos on YouTube channel. So if you go to watch the video, below the video, there is a description part. If you click on it, you will see a link there. If you click on the link, it will give you this PDF, the PDF file of these notes.